Thank you, Professor Derek, for inviting me, and hello, everyone. I will talk about the Valles Marineris rift on Mars. In general, it's when we are hearing about rifting on Mars quite frequently, it's related to Valles Marineris, which is this very big canyon system that we even see in the background here. And I will report on some results that we published in November here, and about the structure of the basement in Valles Marineris and its influence on the development of the rift. So first, let's be clear, there is of course no rift on Mars because there is no plate tectonics, so it doesn't work, but let's call it rift for convenience. Just we need to remember that the implications, of course, on Mars are not the same because it's a one-plate planet. So it's a big thing, 2,500 kilometers. It's deep, up to 9 kilometers, and it's linear. So this is why we can call this in general a rift, because it's something very big, a crustal or even lithospheric, and it's extensional. It's also something symmetric. As you can see here, it's a random profile across some of the grabens. You see that it's topographically symmetric and also structurally. Here we have three main grabens, some layer deposits, and some mass wasting processes along the slopes. And this symmetry is something which is convenient to compare with terrestrial rift. For instance, I have here in mind this paper by Cortier et al. 2018, who showed that the basement fabric controls somehow the symmetry and the asymmetry of continental rifts. And what they show is that to have symmetric rifts like this with two large walls one on each side, you need to have similar lithosphere strength, at least in the main Ethiopian rift. And heterogeneities lead to asymmetry in the rift structure. So since we have this is something which is more symmetric here, does it mean that the lithospheric strength is homogeneous? And so this is a question we'll try to answer at the end of the talk. We work in particular in these two regions, two small regions in red here in northern Valles Marineris. And in particular, we started by mapping the structures at a high resolution. We have everywhere resolution of 25 to 50 centimeters. So we mapped the structures at the scale of 25 to 50 centimeters. And so this is the floor of this graben. So it's two grabens. So this is here that is intensely deformed first. And also there are some magmatic intrusions which are here in red. If we are zooming in one of the regions here, we could identify some C' and S structures with a schistosity here, which is rotated between the shear structures, indicating brittle ductile shear deformation, and also a kinematics, which is right lateral. What is the material which is affected by this? It is in general some kind of bright massive bedrock like here, with fractures more or less dense. And or it can be also breccia, this one. In both cases, it's very different from what we have in the layer deposits here, which are sulfates, and which are these things here at the bottom of the image. And so we have a let's say satellite image on the left here, and this is a principal component analysis image. So this is the type of material that we have. In the other trough system, we also have right lateral strike slip deformation, quite complex, as I said. You can see part of it quite well here. But the most spectacular thing is the presence of fault mega breccia in these two areas here. And look at the scale, the fragments are enormous. It's I think I've never seen any paper reporting breccia fragments of this size on Earth. So we probably have a dramatic event which is recorded here in this mega breccia. Now the composition of this basement rocks. Fortunately, we have a cube of hyperspectral data at one place. And so this cube has a number of near-infrared channels, and we developed a nonlinear spectral unmixing methods to infer mineral mixtures in this cube. We defined three regions of interest, as you can see here, 1, 2, 3. we have the measurements, spectral measurements, either infrared in black, okay, and in blue we have a model of mineral mixtures, including of mineral mixtures plus atmosphere absorption. So we removed for the atmospheric absorptions. And you see that finally we have a very good match between the measured spectra and the model spectra, which means that we are quite confident in the mineralogy that we have here. So what type of mineralogy do we have? We can have two types of minerals. First, primarily minerals of mafic rocks, giving gabbronorite and troctolite, and a lot of sulfates, some of the sulfates coming from the layer deposits, which are very well known. Kieserite is probably coming from the layer deposits by katabatic ruins, for instance. But the other sulfate minerals are more of hydrothermal origin and probably from hydrothermal alteration of the mafic rocks that we have. So this is the type of rock that we have. Now the age is of deformation. All the plateau around Valles Marineris, let's say to be short, is 3.7 billion years old. In our first study area here, so we see this is where we have the deformation. There is nothing outside. So the deformation is occurred before 3.7 billion years. In the other region, this is in white our study area, and we see that the shear zones were reactivated as grabens, narrow graben, which I'm showing here. And also it is just a place where we have the boundary of the Borealis impact basin. So what is this thing? It is just that. It's something which happened probably at 4.5 billion years, a big impact. And it is in general thought that this impact is a reason for the planetary dichotomy boundary, which we have here in this topographic map. So this is the dichotomy boundary here, and we have the southern highlands, very old and cratered, and the northern lowlands, which are several kilometers below the highlands and more recent. So if the Borealis Basin is at the origin of this dichotomy boundary, I mean, if it ever happens, then this is the boundary of the impact basin from inversion of gravity and topography. And we have the same boundary here in red, okay? And we have the shear zones here in green that you identified earlier, and the narrow grabens extending the northern shear zone here. So all this is parallel. Now let's move a bit to the magnetic record. There is a fossil crystal magnetic field on Mars, and we have here the total crystal magnetic field at the surface. So we know that the impact occurred while the internal dynamo was active, and we know also from the Earth that quite frequently around impact craters and basins there are some magnetic anomalies which are concentric and related to hydrothermal processes. For instance, here we have Chicxulub with these annular magnetic anomalies. And so do we have the same here? What we know already that the field is weaker within the Borealis Basin at a global scale, at the scale of Mars. This is what we observe. So in this area here, the field is in general weaker than what we have here in the south. So here it's not that clear because the crust was probably demagnetized later for a reason which I will explain now. At 3.7 billion years, the Tharsis volcanic dome, let's say the Tharsis hotspot, if you like, started to form here. So it corresponds to the red and violet terrains. Okay, and this formation was coeval with the emplacement of dike swarms that we have here. Here we have the orientation of the dikes. Okay, and all this, I mean, all the crust here is completely stuffed by dikes, and probably it contributed to the magnetization of the crust. As well as this lava flow that we have with the dashed lines here, which were erupted from the dikes or from other sources. So it's a little bit more complex here. But now if we are moving from the total field to the radial crystal field, we see that excuse me, the magnetic lineations are elongated parallel to the dichotomy boundary, to the Borealis Basin boundary. So it's fine. We also have some dikes here which are aligned with them. Here are a couple of dikes on the high resolution image. And we have also some mountain ridges here also. I mean, all this is parallel These ridges are more than 1 kilometer high in some areas, so it's really big things. And what we finally have is basically all what we need to make impact tectonics. So if we imagine the effect on tectonic effect on the crust of the Borealis impact, we are expecting all this. If you are thinking, well, it's based on, let's say, for the lunar analogs of Mare Orientale, for instance, where we have also dikes, mountain ridges, which I'm showing right now. They are very easily identified. Concentric magnetic anomalies are from the Earth examples. What we have, of course, fault mega breccia everywhere here. And so the only thing is that to have impact tectonics, we need to have ring faults like we have here in red. So the ring faults basically correspond to these shear zones. What we only need is to generate this shear zone as ring faults, and then they were reactivated as shear zones. So if you assume this, then we have all the elements of impact tectonics. So this is the impact tectonics period, now the Valles Marineris period. And I would like to show you here the results from Andrews Hanna 2012, who was modeling using a thin shell flexural approach the load of the Tarsis magmatic rocks in the crust of Valles Marineris.
That's just over 10 minutes. Just okay.
Excellent. So the load of the Tarsis load in a crust broken by the dichotomy boundary. So this is a grid setup. So this is the southern hemisphere, northern hemisphere, crust of different thickness, and loading by gradual steps of volcanic plateau edification. And what you can see here is that the differential stress is maximum in the Valles Marineris region. So this is a dark red here, and this is a dark red here as well. In black, we have the tensile stress orientation. And so what it shows here is that in the case of loading of Tarsis and formation of Valles Marineris in a crust broken by the dichotomy boundary, then you can form a lot of Valles Marineris here by extension. Okay, with these black lines, which are sigma 3. So this is an important result. And here on this slide, we have the same information, just I replace the black sticks, the sticks by arrows to show extension and compression, let's say, to be short. So, and just to show that if we are doing Valles Marineris by extension, then the shear zones also can form with the same trajectories of principal stress. Okay, here and here for these two shear zones with this stress field, you can form the shear zones as well. Just if you have a permutation of stress, you need to go from sigma 2 vertical to sigma 2 horizontal, but the orientation of the principal stresses do not change. So we have an enormous amount of information here, actually, and I will now try to synthesize this shortly. This is the initial situation here with the planetary dichotomy boundary related to the Borealis basin. What we could identify is these features, mountain ridges associated to the impact basin, the dikes formed, and ring fault with the mega breccia parallel to the ring faults. Then we know that actually initially the very early surface load was in the south here. This is where things started. So what happened here that this load, of course, generated some stresses in the crust, and what we can infer is that the differential stress here was big enough to for the small circle to cross the friction low, and then these ring faults were reactivated as strike slip faults. Then the Tarsis hotspot developed, and the loads developed dramatically. Basically, all the red which you have here corresponds to Tarsis magmatic loading of the crust. Okay, so what happened here is that with this increasing magnetic load, we increased the differential stress. So this white arrow here, and as part of it, we have flood lava eruption, which is loading the crust from the top, which means that at the top of the crust, we are moving sigma vertical to sigma 1. Okay, and then we are gradually putting the crust in extension, and this is what we have here. So sigma vertical went to sigma vertical here, so from sigma 2 to sigma 1, and we are tangenting now the failure envelope, and here now with this new big load of tharsis, we can form the gravens of Valles Marineris as well as the dike swarms which are propagating at the same place. So this is a quite simple scenario of evolution, and we can now go to the question that we had at the beginning. Following Corti et al. 2018, we would think that basement heterogeneity did not play a significant role in the development of the reef. So the question, I mean, what probably happened, if this is correct, is that the Borealis basin, when it formed, just weakened the whole crust in Valles Marineris homogeneously. So we have still an homogeneous crust, but much more weak than before. And so we have, this is why we have a symmetric gradient in Valles Marineris. The crust is still homogeneous, just it's weaker. Our activation of basement structure, then here it is quite original, because the basement structures, I mean the ring faults of the Borealis basin were reactivated, strike slip. Okay, but since we are on a one-plane planet, you cannot do strike slip vertical shears for an indefinite amount of time. At one moment, it needs to stop, it needs to lock, because there are no plate boundaries. The boundary conditions are not adapted to this. So when the magmatic load of tharsis here increased, then the strike slip deformation stopped, and the only possibility was to open rift faults. And so what's interesting here is that the orientation of the oblique structures in the rift is okay, but they are just locked at the moment where the rift forms, which is quite different from what we have in many continental rifts on Earth. Thanks very much.
Thanks, Daniel. Excellent. Are there any questions? If you've got a question, to stick in the chat or raise your hand or just speak out. So if there are no questions, I've got a question. What is the kind of scale of these dikes? Like, how deep do they go, and what are the constraints on that, and what's the origin of the magma?
These ones here, you mean?
Yeah.
The longest one. So the thickness is up to, I would say 100 meters, more or less something. They are not easy always to identify, but it's the maximum is on the order of 100 meters. And they probably originate from here. We do not see it very well because the color are not very adapted for this, but there is a kind of dome here. And so you see here, the early tharsis load is located here in the middle, here in the south of Tharsis. The second step was to have an uplift in this area, and at that time, the dikes were propagating to the outskirts of the dome in this area. So this is the source, but we don't see any volcanic edifice, any big thing, for instance, which would correspond to a single magma source, which would be obvious here. It's just this region.
There's also a question in the chat about the ages. How are the ages determined of the dikes? Is it?
It's of course an excellent question. What we can say only is that the dikes never go completely to the surface of the plateau. We see them on the slopes of the graben, and they are going to a maximum elevation which is several kilometers below the surface of the plateau. So they stop let's say halfway on the slopes. So they are not very young, they are not very old. It's very difficult to constrain. Finally, the main constraint is geometric. We see here that the dikes converge toward this area. So we have the volcanic activity of this region, which can be dated by crater counting. And then this age gives the age of the dikes. I think it's the best constraint that we can have so far.